On the power machine, you get a file forsete.output, and it can contain one of three things: either compiler complaints, or runtime complaints, or output from two programs, size and objdump. Objdump means object file dump. Okay, and I will explain size and objdump plus two other programs. Now, okay, so let's look. What do we have? We have one global variable that is initialized, and one which is not initialized. I mean, it will be set to 0, and one variable on the stack. Okay. First, I will show that we use version 10. We can do that like that or like that. Okay, and the reason for that is that in May 2020 and October 2020, first GCC and then Clang changed the behavior of B. That's quite surprising, but it's true. Okay, I will come to that later in the lecture 7. Okay, but I just want to point out that we use this version for what we will see now. Okay, so let's compile it, and now we get an object file a.o. We can ask, this is an ELF 64-bit relocatable file for the power machine. Relocatable means not complete program yet. It's just part of a.out. It will be a part. Relocate is a really stupid name. It does not relocate anything. It just assigns addresses later on, but that's a different story. So if you find relocate confusing, don't bother about it. Okay, let's use size. What does it say? It says that text is 200 bytes, data is 4 bytes, BSS is 4 bytes. And this is, of course, the sum of this in decimal and in hexadecimal. Okay, so let's see why this is the case, why this is the output. And we will go to this figure that I like to show in various ways. So this is the memory layout of a program. And first we have instructions. And this is, due to historical arrests, called text on Unix systems. And the reason it's not only called instructions is because there can be other non-modifiable things in this area. Okay, so it's just called text. And after that, oops, there should not be anything. Let's forget that that one exists. Okay, then we have the data. And that is initialized variables with static storage duration. What's that? It's global variables that are initialized at compile time and static variables initialized at compile time. And which variables are put in that area? Well, it's only A. So now we can write A here. And it was 1, if I don't remember completely wrong. So here we have a 1. And okay, so this view is both from when the program runs and a view of this file. Okay, so here is A. C, it's not anywhere in the file since it will appear when the program runs, and it will be in the stack, and there will be a 3. Okay, and B is not initialized, so it goes into this part instead. This is only for global data, static storage duration, which have a value that is non-zero. Okay, so the B will be here, but in memory, but in the file, it's not, this 0 is not stored. And the reason is, well, what could it be? Well, storing 4 bytes for this int, it won't be a big deal. It could even, if the compiler wants, it could store it here and write the 0 in this file. But as we can see a warning of here, if we have a huge matrix, for instance, then there is no point in storing all these zeros in this file. Okay, so instead this BSS part contains data that will be set to 0 when the program starts. BSS, sorry, BSS means block started by symbol, and as text, that's a historical rest, that name. What it really means is data that will be initialized to 0 when the program starts, which was a bit far from BSS. Okay, then we have the heap, and it's not included in the size command, output from the size command, since, well, we have not allocated anything, and I mean we cannot know anything how much the program will allocate. So it's just the static data that is used, not dynamic data from malloc. Okay, and well, that one would grow and the stack would grow in the other direction. So the size command only refers to this. This is the size in total. Okay, so and that's also the score in the RPN, Word and Poly assignments. Let's see if we can do something here, such as we can okay, so we have BSS 4, and that's due to this B. But what happens if we change this to static? And we can remove the initialization. Oh, and we can keep we keep the initialization and recompile. The AND means we do this command only if there is no compilation error. Okay, so now what happened? The data increased as expected, since now C is not on the stack, it's in the data section. Okay, and BSS is still the same. Oh, we can move this there, and it should be still the same. Okay, so that was that. Objdump. It has numerous parameters, and we will use -d and -t. Let's use -d first. D means disassembler, so we will this program will interpret the file and show the machine code. So this is what it finds. And okay, so it starts with saying that what kind of file this is, and this is the machine code. Starting from address 0, and that means offset in the file. Since we have an a.o file, I mean a real so-called relocatable file that will, this is not executable, we cannot run a.o, we have to merge it with the printf, etc. to get an a.out, and then main will be at a different address. So this add immediate shifted is put in as the first instruction in main, but it will not be at that address. Okay. Let's look at another program, nm.o. That's a command to print the symbol table that is, well, we will see. It says here D is in data, and it's a global variable. So this one, if it has a capital character here, it's not static. I mean, this is like an external symbol. Okay, and the B as well, and this is C, which has static in here. Okay, what else? We have main. It's capital T for text. Actually, what these characters mean is which section in the object file they are located in. Okay, we can see which sections there are. Okay, so we have the text, data, BSS, read-only data, and some other things, which we don't bother about. Okay, let's look at the more symbols. Printf, it's U, which means it's undefined, since it's not defined in this file. And when we create the executable file, we have to find it somewhere. And then there is also this table of contents. This is, as we can see, it's a 64-bit machine. And to create a 64-bit constant, and which we need when we want the address of a symbol, then we need 4 instructions, since each instruction contains 16 bits of constants. Okay, and that's a bit inefficient to read the value of a variable, global variable. Instead, there is an array with addresses in each file. Okay, and then we will use. Well, we will not go into the details, but this is an more efficient way to find the address of a symbol. Okay, so that we don't have to use 4 instructions to get the address. Okay. If we compile this like this, then we can obviously run the program. And if we now type nm a.out, we get all the symbols in the program. And this is a lot. Okay. Let's look at the size of the file. It's like that. Okay. This file a.out does not contain all code. It does not contain the machine code for printf, for instance. Okay, let's no, we don't have to do that. But what we can do instead is to compile with static a.c. Static is used in numerous places, and when it's used on the command line, it means that all library functions should be included into a.out. So if we look at the size of this file, it's much bigger. Okay, and the reason is that the linker included all functions, runtime functions, what the printf uses, etc. into this file. Okay, what we can do now is to look at what's in there, and there are lots of symbols that are used. If you distribute a program commercially, you may be worried that somebody would read this. I mean, you can get the machine code and try to reverse engineer it. So let's do that. It's not the most important program to reverse engineer, but we can do that anyway. Okay, so let's see where main is. Here it is, and we can see that it will call. This means printf, but it has a slightly different name. Okay, and then we can try to understand what the program does. But if we don't want that, we can use another command called strip, which removes the symbol table. So let's ask for the symbols. No symbols. And actually we can repeat this. Well, first of all, we can check that it still works, which I'm sure it does. Okay, and now we can do this again and look at the file, and we will not find main. Yeah, well, we should not. Okay, not found. Not found. Okay, if we remembered the address, we could go there, but now this is harder to reverse engineer and try to figure out what this does. But this is the basic way to reverse engineer a program, namely dumping the assembler code. I mean, it's quite obvious that this is the way. So you dump the machine code and try to understand what it does. So this is much more complicated if we have used optimization, because then the machine code will not be so easy to understand. If we use a Java class file, it's much easier to go from the class bytecode into something that is understandable. Okay, so I will not ask anything about this in the oral exam. This was just a request on Discord to explain this file. If there is interest that I should make another optional video for explaining how linkers work, please write that in Discord and I can do it, but it will not be included in the oral exam.